All right, so let's get on with the lecture, guys. 18 people. That's pretty interesting. And after class, if you have questions, we can discuss those. So guys, what you do now, just as a warm-up, establish this property and try to explain why it holds. Y is logarithm base A of m times n, the same thing as logarithm base A of m plus logarithm base A of n. Please establish that as we wait for the rest of the class to join. We actually established that last time, Francis. Yes, David. Well, here you go. You see, guys. All right, Anna. Sorry about it. So, guys, this thing, it's something that if you are aware of exponential laws, you should be able to come up with your own device, your own knowledge. So what do you know? You know that, for instance, a to the power of log base A m times n, this is equal to what? Type in the comments. I want to see lots of comments now. Okay, Francis, here you go. This is equal, a to the power of log base A mn is equal to m multiplied by n. And then those separate numbers, how can I write m? I can write it as a to the power of log base A of what? What do I put here? There should be, how many students are here? 23 comments. M. Very good. M times A log A n. And what's the result? The result is A, because we add the powers, log base A m plus log base a n. Yes? Not hard, is it, guys? If you understand what it means, not hard. Now, this is, of course, the difficult issue. I do not know how many of you realized I kind of gave a rant or a speech about why logarithm must exist, at least in the case of the natural exponential function of e to the x. Yes? I think maybe a few people, maybe Humira, maybe Tzvi, maybe Zakaria, maybe Darul, I'm not sure, right? And Christiana, she is not here. They might have understood it. Good, and maybe Jahin understood it is also, I think, right? So, the logarithm is, at least for real numbers, is unique. There is only one power that can do that, and that means that since this power does it and this power does it, it means that they are the same. Do you see? Because we have two expressions that appear to give equality, they must be equal expressions. So I used exponent laws for that. I can similarly establish the formula for log base a m divided by n, that it's equal to log base a m minus log base a n. Now, could you establish, please just do that again, try to write some sentence in the text that I know that you understand it. Tell me, please, what can I do here? If I have log base a m to the power of r, what can I do with r, please? Tell me, with the logarithm, that's very important. What can be done with this r? Take it out, well, to be more precise, to what? For wine? Put it in the front, that's very good. This is the same as r log base a of m. Exactly. So could you now please establish that this property is true? Assuming uniqueness of an existence of logarithm. Let's see. Okay. Well, yes. I hope that means you understand, guys. So what do? You simply, when you want to understand it, you say, okay, well, a to the power of log base a m r, m to the r, this is what? This is the same as m to the power of r, which is the same as a log base a m all to the power r. And here I have property of exponents. I can take the r and multiply. So this is a r log base a m. And now again, I see that they are equal. Yes? So that establishes the property I wanted. Now, then there is a very important situation, guys. If you understood, there is something very special about the e to the x. Using calculus, we can show that for any n bigger than 0, the equation e to the x equal to n has a unique solution. Yes, that was the thing that I mentioned before. So how do those ideas come together again, guys? Why e to the x? We know that the derivative of e to the x is e to the x, correct? The function is not changed. What is e to the x, guys? I'm not sure how you think of it. I do not think of exponentials at all, right? I think of e to the x like this. I think it's 1 plus x plus 1/2 x squared plus 1/6 x cubed. This is for me e to the x. So if you say e to the x, I don't see that. I see this. Yes? Because if you understood, guys, that's a bit more technical. If you understood the derivation, what function has derivative equal to itself? This is the infinite polynomial that satisfies this property. Take the derivative of that infinite polynomial, you have itself. You see that? Now you can, and I do that in the notes, you can in many ways show that that this function, this infinite polynomial, behaves just like we expect exponentials to behave. So if this is our infinite polynomial, let's just call it p of x. Then I can prove that p of x plus y is equal to p of x multiplied by p of y, and that works for any xy. Do you understand? So this is what the exponential rule amounts to. You see, when I say e to the power of x plus y, when you say the exponential rule is e to the x, e to the y, right? This is easy to establish when this is an integer. If this is m plus n, this is obviously so. Yes? But how do you establish that for any other numbers? How do you make sure that using any other numbers, this entire expression even makes sense? Are you with me, guys? I know a few of you are, right? I mean, some of you, I think, confused. What is it talking about? Polynomial, exponential? I'm entirely confused, right? I'm saying that when you begin doing this process, right? When you try to explain what is the power rule, right? So when you say something like 2 to the power of 3, when it's explained in school, you understand it as a bookkeeping. It just as something you write in place of writing 2 times 2 times 2. Yes, but what is an exponential in general? That becomes already more and more complicated. Why would those rules always hold? Now, if you establish this e to the x thing, if you establish, if you find a function whose derivative is itself, you can completely logically build up those properties. You can build those properties, and you can verify that p of x plus y is p of x times p of y. And you can understand what it means to take e to the power of pi, for instance. That just means 1 plus pi plus 1/2 pi squared plus 1/6 pi cubed. It doesn't mean to multiply e by itself whatever number of times. You understand? So I can come up with a function that behaves like an exponential function that I expect in all instances where exponential functions are understood, and extends the notion of exponential functions to any value. Good. So so what is this function? This function e to the x is clearly, look at it. If for any x, you can prove then that for instance, you can prove that. How should I say that? You can then see that, for instance, that e to the 0 is 1 plus 0 plus 1/2 0 squared, blah blah blah. So this is just equal to 1, to 0, to 1. And so for any we can say e to the 0 equal to e to the x minus x, which is going to be e to the x times e to the minus x, from which it follows that e to the minus x equals to, and this is 1 here, equals to 1 over e to the x. Yes? So that means that it's always positive. That means that e to the x always positive, no matter what x. If you put a negative number, let's say, what is e to the minus 3? That's 1 over e cubed. What is e to the minus pi? This is 1 over e to the pi. Do you understand what I'm saying, guys? I mean, you might think I'm saying either something very obvious, or you might think that I'm saying something very mysterious. Now, do you understand what is e to the minus pi? This is what I'm saying. Look at it, why it's not obvious. What I'm really saying is that if you take 1 plus minus pi plus minus pi squared times 1/2 plus 1 over 6 minus pi cubed, so on and so forth, you will get the same thing as if you take 1 and divide by 1 plus pi plus 1/2 pi squared plus 1/6 pi cubed, and so on and so forth. Do you understand what I'm saying now? Right? There is, you know, what I'm trying to say, which is maybe very hard for some of you, is that exponentials were, until you establish them through something like this, are pure fiction. Right? E to the x is like the first exponential, you might think, that you understand. Right? That's what it's doing. So what I can observe is then that derivative of e to the x is e to the x, which is positive. That implies that if I try to look at the graph of e to the x, the graph of e to the x is differential. I mean, it's made of many line segments. Those line segments are all pointing upwards. They all have positive slope. Derivative is just the slope of the line segment. You understand? So when the derivative is equal to 5, why do I see a line? If the derivative of a function is equal to 5, it's a line. Do you see why it's a line? Because it means for every x you look, the slope is not dependent on x. It's the same, or each line segment that builds up the curve has the same orientation. Yes, that's the idea of calculus, is building things with Lego blocks. Good. So this is so the fact that the function, that its derivative is equal to itself and the function is positive, means the function is increasing. Which means that if you take e to the a, it's going to be less than e to the b if a is less than b. It's an increasing function. Are you with me? Now, what can I do next? Yeah, I hope you are, guys. It's amazing if you are, okay? Don't be nervous. It's all good, I hope. If you are with me, then you are, it's amazing. It's just very great. If not, it's okay. So we have another thing that we observe is that e to the x, which is equal to 1 plus x squared, 1/2 x squared and whatnot, this is bigger than x, which means that's a sort of like squeeze theorem, but I'm squeezing to infinity. Limit as x goes to infinity of e to the x is bigger than or equal to limit as x goes to infinity of simply x. And that means infinity, which means e to the x goes to infinity. It's an increasing function, which means once it passes a certain value, it never comes back to that value. Yes? Which means what? Which means that if now I can use the intermediate value theorem. Here is the number n. Here is let's say here is the number 1. E to the 0 we know is 1. Now at 0 I can select a value. Let's call this value a. For some value a, e to the x will have to be bigger than n, because we have that e to the x goes to infinity. So for some value a far enough to the right of 0, e to the a has to be bigger than n. So there should exist e to the a bigger than n. And then you see what happens, guys. Because it's an increasing function, we have that there must be a crossing. That's by intermediate value theorem. That's how those theorems can be used, okay? So the crossing happens at that point x. So we have that e to the x equal to n, which means that labeling x as log base e of n makes perfect sense for this proof, as I did it for n bigger than or equal to 1. But you can extend it in the other direction for all n bigger than or equal to 0. I just showed you how to prove that there is a unique logarithm for all values n that are bigger than 1 in the case of exponential logarithm of e to the x, I mean, right? Natural exponential logarithm. So this function, log base e of n, is so important that we give it a name. So we will say that log base e n, we will call it ln n. That's the name. So ln just means base e. Good? Now we can finally return to derivatives again. By the way, all other logarithms, that's change of basis. Number 4 property, all logarithms can be represented in terms of the natural logarithm. You understand? So every other logarithm can be viewed as some quotient of base e logarithms. So that's a very useful idea. Let's try to see how we might take the derivative of 2 to the x again. Remember how we tried to do it before, guys. 2 to the x, we viewed it as limit as h goes to 0 of 2 to the x plus h minus 2 to the x over h. I could factor 2 to the x plus h, and I could factor 2 to the x, and I have this limit. And we could not evaluate 2 to the h minus 1 over h. We kind of said it's about 0.696. Good. We kind of did that, but now we can do something much better. We can actually give this limit explicitly. Here, guys, is here is a question. When you take the derivative of 2 to the x, what instead would you have preferred to differentiate? You see, it's wishful thinking. I am dealing with this problem, but I prefer another problem. Very quickly, what would I prefer to differentiate? Well, it has to be similar enough, right? I mean, yes, maybe x squared is nicer, but you know, e to the x, yes? So then what I can say, this is the derivative of e, but if it's not e to the x, it's what? E to the power, how do I get this number? It's just ln of 2 to the x. You agree? Why? Well, you'll see hopefully why. Do you see that I prefer to have e as the base? When I have e as the base, then I know everything about the derivative. I built it up. So what is that? That's the derivative of e x ln of 2. You see what I can do? I can take the x and drop it down. Yes? That's what we established. Hopefully, guys. I mean, I'm hoping you understand at some level, and the deeper the better, why logarithms exist from the point of view of calculus. Okay, so what's the derivative of e x ln of 2, please? Tell me what's the derivative. Okay, well, there should not be division by, look at it. ln of 2 is just a number. Whatever that is, it's just a number. It's the number that must be placed in e to give 2. Yes? So e to the derivative here is what? It's just it's chain rule. It's e x ln 2 times the derivative of this expression. Think of ln 2 as maybe like the number 7. So it's like 7x, x times some number. So what's the derivative? It just x disappears. It's times ln 2. Are you with me? No. How is it? So the derivative of e to the some function is e to the function times the derivative of the function. Yes. So it's ln 2 here. And what do we get? And look at this, guys. E to the x ln 2. It's just 2 to the x. So the answer is 2 to the x ln of 2. You see that? So what do you observe, guys? What is, remind me please, what is limit as h goes to 0 of 2 to the h minus 1 over h? I don't mean what it equals to for a moment, but what is that limit expressing? The limit is what? Yes, derivative Zakaria, wonderful. Derivative of 2 to the x, where x is 0. Yes? You should right away, all of you have the same instincts. Like you look at this limit, it's the derivative. The derivative at 0. So this is just the derivative of 2 to the x, where x is 0, which is what? Which is 2 to the 0 times ln 2, which is therefore ln 2. So this limit is precisely ln 2. Do you see that now? Guys, and we speak about the same question, you know, how many times already? Like, that's why we move so slowly. It's like I repeat the same idea a million times. Like we had 20 lessons, I think I repeated it 20 times already. So get with the program. Tell me now, please, do the derivative of 3 to the x and do that in the same process I have established. What's the derivative of 3 to the x now? All right, very good. Of course, guys, not just because you notice this pattern, you're able to establish it from scratch, correct? It doesn't take much to establish it from scratch. What is this? This is just, you have to understand, I know how to take derivative of e to some power. So it's e to the power of ln of 3 to the x, which is the same as the derivative of e x ln 3, which now I understand this is ln 3, guys. Just don't be scared of it. It's just a number. Just a number that I hope you understood how using the properties of derivatives, the properties of continuous functions, intermediate value theorem. I know that ln of 3 exists. I don't know what it is, not right away, but I know there will be a number like that. Yes? So the derivative of x ln of 3 is e x ln 3 multiplied by ln 3, and this thing, it's nicer to move it back. Look at it. It's the same function as 3 to the x. Do you see it? 3 to the x is this function. It's this function. So it's just simply just note, guys. Write in your, if you're writing notes right now. Do you see this? Do you see that it's the same thing? Do you see that this is the same thing? Right? Same thing. So the result is 3 to the x times ln 3. In general, naturally, you can think the derivative of a to the power of x is a to the x ln a. Yeah? So that's what we have. And of course, then we have this new expression. We know that the derivative of e to the x is just like another, it's just the same as e to the x ln of e. But ln of e is what? So this is e to the x log base e of e, and log base e of e is 1. So it's still the same thing as e to the x. So there is no conflict with our prior formula of the derivative of e to the x. You agree? The more general formula works for everything. You see, the logarithm ln takes a special role. E takes a special role. Why does e take a special role? Because this function e to the x, its derivative is equal to itself. It's very important, right? Functions whose derivatives are not changing them are tremendously important. All right, so let's do some calculations, guys. Please help me with this problem, okay? I want you to take the derivative of 3 to the power of tangent x. What will you get? Very good. Francis, you made one small mistake. Can you find it? No, it's good. The second squared is good, Francis. Very good, Jahin. ln3, right, you can stick ln3 somewhere, right? So what's the answer? Derivative of the outer function is 3 tangent x times ln3 times the derivative of tangent, which is secant squared x. Yes? Now tell me, please, what's the derivative of, well, let's say of secant of 5 secant x? All right, let's see what's the derivative, guys. So the derivative of secant is secant tangent. So it's secant of 5 secant x tangent of 5 secant x. Yeah? Then times the derivative of 5 to the secant x. So it's times 5 secant x ln 5 secant x tangent x. Good. You see? Now what's the derivative of 5 to the power of 3x? All right. Very good. So the answer is 5, 3 to the x ln 5 times 3 to the x ln 3. That's it. Good. You have some more here, but you get the gist. Okay, so this is now a new type of derivative that you can execute. Before we took the derivative of 2 to the x and we said 2 to the x times some number, right? But now we actually have a way to name the number. And that's a big progress. Now let's go back, guys, to implicit differentiation. Do you remember it, guys? Not completely forgotten, I hope. Yes? So what's the idea of implicit differentiation is that very often, and that's actually the most frequent application of differentiation in physics and in other sciences, is that you don't get the function, but you get a formula in which an equation, to be precise, in which the function is hiding. So a simple illustration of that, we had a circle, and the circle is given as x squared plus y squared equal to 25. And let's say we want to zoom in at some point of the circle. You remember this point is not 5, 5, it's 5 over root 2, 5 over root 2, right? So this is 5 over root 2, 5 over root 2, not what I wrote. Good? Now I want to zoom in at this point and I ask myself, is the curve differentiable? What am I really asking? I'm asking, if you zoom in at that point, will you be seeing a straight line? And if the answer is yes, then the curve is differentiable. And this is very historic. You already understand, guys, that for thousands of years, people assumed the Earth is essentially flat because they were understanding that, well, they were not understanding it, but they were seeing the stand double. They were seeing the tangent approximation. Yes? So when you zoom in at this shape, it would start looking like a straight line. We already did it many times with the computer. You believe me, I hope. Good? So how do we find the slope of that line? Or how do we find the equation of this line? This line that becomes indistinguishable from the circle. Even though the circle is globally not y a function of x, or x a function of y, we can look at this point locally, and locally this curve is a y a function of x, which I actually solved. Right, so we solve it explicitly. We just solve for y squared, and we get that y is, because y is positive, it's the positive square root of 25 minus x squared. The fact I have plus or minus indicates that y, there is ambiguity in how you define y. But if I zoom in at the top point, yes, then that's what I use. Now, let's suppose, guys, I just to be sure that you are with me, at this stage, let's suppose I pick this point, and this point is 5 over root 2 minus 5 over root 2. What I'd like you to please tell me is if I were to zoom at this point, what formula would you use? How would you find y explicitly? Tell me what it's equal to. Yes. Then, so I want more answers, guys. What would be the explicit formula if I zoom in here? I zoom in at this point. I want y of x. What is y of x equal to? Well, Jahin, we'll get to your concern in a moment, right? So usually when you do that, you are presuming you have a point, and you presume that for that point you have a function. But let's wait with that. Suppose we want to zoom in at this point. We have y of x equal to what, guys? It should be taking you a second to say. The question is, what is the explicit formula of y that I would use if I'm zooming in at this point? If I were to carry explicit differentiation, I first have to have a formula for my function, yes? What would that formula be? Yes, the same but negative. I mean, you're not typing because it's obvious, or you're not typing because you're lost. I need to know that, guys. So it's what? So we solve this equation. We just have y squared equal to 25 minus x squared. And so y, because look at it, here y is negative. Do you see y is negative? It's below the x-axis, so it's negative root 25 minus x squared. Do you follow? That's very important, guys, for you to realize that when you are zooming in at a curve, be it very complicated curve, in theory, there would be a formula for it. Maybe the formula is very scary, but it would be an explicit formula. So this is, we're zooming again at the point, not this one, but at the point 5 over root 2. 5 over root 2. So here, when you do it explicitly, the derivative of y is 1 over 2 root 25 minus x squared times minus 2x. Take the derivative of this function by chain rule. You get this. And then you simplify, you get minus x over root of 25 minus x squared. And observe something very important. Look at it, guys. The expression on the bottom is just y. It's just a function y. So my formula in terms of the original function is minus x divided by y. And so if I plug instead, if I plug 5 over root 2 instead of x and 5 over root 2 instead of y, I wrote here 5 and 5, but it doesn't matter. The same number over same number will give me here minus 1. Do you agree? So that means that the slope is minus 1, and that means the equation or unequation of the tangent line can easily be obtained. What is that equation, guys? The equation is y minus 5 over root 2 equal to minus x minus 5 over root 2. Agreed? That's an equation of a line that will be tangent at the point where I zoomed in. Now, implicit differentiation just requires a little more imagination, but look at it. We do not bother solving. We just pretend that we have a formula here. That's why I wrote it as y of x. I pretend that I have solved, and I pretend I actually see the formula. I pretend that I see, my vision is not good, but there is a formula there. So what's the derivative of that expression? The derivative of x squared plus y squared is then going to be the derivative of 25. Now what's the derivative on this side? It's 2x plus 2y y prime. You see where the y prime is popping up? Because we have the function squared. So the function squared, the derivative is 2 times the function, the derivative of the function. You're with me? And observe what I just do, and it's equal to 0. So when I move things about, what do I obtain? I obtain that y prime is, just isolate this part, right? Move the 2x across the equal sign, you get minus 2x, and divide by 2y. This is what you get. And you get minus x over y. And again, you get the same formula that we obtained with explicit differentiation. Exactly the same formula. Good. So now I would like you guys to work with this function. We already did it, but let's see if you remember. The new function, we are zooming in at the point 1, 2. I want an equation of the tangent line, and here is the equation that defines my function. Please figure out explicitly what is the tangent slope? What is the tangent line? So it should be the equation of a line explicitly. What's the equation of a line? All right, thank you, Tzvi. Thank you, Humira. Guys, you should all recognize that the expression here is y squared minus 4xy plus 4x squared equals 0. This is a perfect square. Okay, Maria Carla, thank you. It's a perfect square. Yes, perfect square means what? Means this is y minus 2x squared equals 0. The only thing that can work is that y equal to 2x. That's the only way that can equal to 0. Good. So this weird looking quadratic equation actually defines just a line. So what's the tangent line? It's the same line. No need to do any work, right? So the explicit formula for y of x is y equals to twice x. Do you all see that? Within this formula, once I am solving it, the explicit formula is y of x is 2x. And there is explicitly in this case the easiest thing to solve. Yes, because now I know at any point where I zoom in, it's going to be the same tangent line. Now let's do that implicitly. Can you do that implicitly just for fun, so to speak? Find the slope of the tangent line at the point 1, 2 implicitly. In other words, where you did not bother solving for what y equals to. Okay. That's very good, Jahin. And you can simplify that slope. Uh, 2x, Francis, right? So so not 2x, but you mean I see. Yeah, so you can simplify it. Good. You can simplify it then. Okay, so here is the solution, guys. Implicitly, you take the derivative of y squared plus 4x squared and the derivative of the other side. So the derivative of this side, remembering that y isn't y. Y is some formula that only has x. We just don't know it. So the derivative of y squared is 2y prime. The derivative of 4x squared is 8x. Here, I use product rule. So it's 4y plus 4xy prime. Now I will bring together everything that has a y prime to the left and everything that does not have a y prime to the right. You see that? Then from here I can factor out a y prime. And I get that y prime is 4y minus 8x divided by 2y minus 4x. Observe that numerator is just twice the denominator. So the ratio simplifies to 2, right? Because we have the ratio that this y prime only is meaningful where the denominator is not equal to 0. So I can simplify it. I just factor out the 2, cross it out. And the result is simply 2. The only way the slope is always 2 is if I'm having a line. Right? The slope will change with x because the microscopic line segments will have to change orientation if the curve is not a line. Clear? Now, here is the next stage, guys. Suppose you were given this formula, x cubed plus y cubed equal to 6xy, this equation. And you have to find an equation of the tangent line at the point 3, 3. Here is what would have happened if you tried to solve it explicitly. You would realize this is a cubic equation. First of all, it would be pretty impressive if any one of you knows how to figure out a formula for the cubic equation. If you're interested, I can show you at some point in office hours how to do that. But it's not easy, right? It took quadratic equations were known for thousands of years in one form or another. Cubic equations were only solved maybe 400 years ago, 500 years ago. Some people came up with a method. Once you get to degree 5, only in the 19th century was it proved that you cannot come up with a general formula in terms of radicals. So degree 5 or higher, you cannot even find a formula. So if you did find the formula for y that satisfies this equation, here is one. Do you see it? It's very scary looking, very long, and it would be tremendously tedious to take derivative of that. You see, it has cube roots and square roots and different access to different powers. Look how ugly and long it is. And this is a very easy equation. It's not very difficult equation as they come. You know, I mean, usually they are so difficult that it's impossible to find an explicit solution. Okay, so instead, let's try to work with implicit differentiation here. Are you ready? So I pretend I came up with a formula for y. If I did, it would look something like this, but I pretend I have come up with it. So I take the derivative of the left part and I take the derivative of the right part. This is what I obtain. 3x squared plus 3y squared y prime equals to 6y plus 6x y prime. I take together the y primes. You see that? And I factor it. You see, so I move this across and factor. All it is, and I move whatever is not having a y prime across. Good? You all see this line. It's just algebra. And then I say that y prime is numerator divided by this expression. Now, when I plug 3 and 3, look what I get. This number, look at it, across, and this number across. This must mean that the ratio is -1. They look alike, just one is the negative of the other. Do you see that? So the ratio is -1. So without getting to the formula, I was able to find the slope. So implicit differentiation is very frequently the best way to go, because you skip figuring out how to solve this function, because A, it is very difficult, sometimes impossible. You cannot come up with a nice formula. And even if you somehow solve something, the formula is going to be horrible. This is an equation of the tangent line. All right, guys. Here is your new task. Find y prime if we have sine of x plus y equal to y squared cosine x. This is an equation where doing it explicitly will be very difficult. Where did the y prime go in the previous question? Here it is. Look at it. I kept it factored. You see it? So I just move everything that has a y prime to the left. Everything that does not, I move to the right. Then I'm able to factor the y prime. And I have this. Good. So now you have to find the derivative of y, just a formula for y prime as much as you can. If the equation that defines y is sine of x plus y equal to y squared cosine x. I'll be back in a minute or two, and afterwards we'll do a competition. Who can do it faster, me or you? Let's see, we'll see how fast we can do that, okay? Well, how are we doing? I don't see the answer yet. Let's see what it should be. All right, so we have sine x plus y squared cosine x. So the answer should be, let's see, y prime equal to minus. Here we have cosine x plus y minus, well, plus y squared sine x. And on the bottom, cosine x plus y minus 2y cosine x. Yeah. Okay, so let's see, on the bottom 2y cosine minus 2 cosine x plus y minus 2y cosine x. There is some Tzvi, you almost have it. I think there is some mistake. No? Let's look at it. Here is what you do, guys. So derivative, yes, derivative of the sine of x plus y. Derivative of sine x plus y is going to be what? It's going to be cosine x plus y times the derivative of what's inside. What is inside? Inside is x plus y, so the derivative is 1 plus y prime. Everyone understands? You just have to be careful with applying the chain rule here. Derivative of x plus y is 1, because I know to take the derivative of x, plus I don't know what this function is, so I just say y prime. And here I apply product rule. So what is the derivative of y squared? It's 2y y prime times cosine x plus y squared. Derivative of cosine is minus sine. And here I just, look what I did here. Here I factored out the y prime, and here I just wrote minus y squared sine, right? And here I distributed cosine x plus y to 1 and y prime. Are you with me? Guys, everyone is understanding how I got this line. Again, I'm explaining algebra. And then what do we get? Then we factor out, we look at it. Then I move everything that has a y prime to the left, and everything that does not, I move it to the right. So here is cosine x plus y. I moved it to the right. It became minus cosine x plus y. I have 2y cosine x y prime. I moved it across, so it became minus 2y cosine, right? So we have, this is my factoring of y prime. Second to last line. So this one, yes? It's just I distribute cosine x plus y to 1 and to y prime. Do you see? It's just a parenthesis of 1 plus y prime. I distribute it here, and I distribute it here. And here I just move the minus in front of y squared. And I decided to factor out y prime, and I just wrote it this way. So then once I move everything around, I have something times y prime is equal to something without a y prime, so I just take quotient. So y prime is this divided by that. All right, guys. Let's do a competition. What do you say, right? I'm going to show you a question, and we'll see how fast you solve it. Good? So here is A. 2x cubed plus x squared y minus xy cubed equal to 2. Let's see how quickly you can solve it. And I'll compete with you. Ready, set, go. I'm done. Giovanni, not fair. Why? It's Svi. Let's see what Svi is saying. Yes, you're right, Svi. If you're done with one, right away move to the next one. Don't wait. Well, just negative is, I'm not sure what you mean. Yes, you can move the negative in, or you can move it. You can just multiply the minus anywhere you like. What do you mean by a positive answer? What do you get, Francis? write what you got. I'm not sure what you mean by positive. I mean, you could have written it this way, minus 6 x squared minus 2 xy, and here you could have written maybe y cubed. So that might look positive to you. Six x squared, I think you mean. There is some mistakes there, Francis. I mean, maybe typos or whatnot. So it should be what I have. Right, what are we doing, guys? Are we doing A or B? Where are we now? Oh, you're doing C already. It's okay, Giovanni. It's a difficult topic, one of them that does get kind of a bit annoying until you get very comfortable with it. So here is, guys, here is how B is solved. Look at it. So y prime is equal to it's equal to 1 minus e to the y divided by x e to the y minus 1. Yeah. Let's do C. How quickly can you do C? Let's see. So that would be y prime equal to x y squared minus one over 2 root x plus y divided by 1 over 2 root x plus y minus 2x squared y. So are we competing, guys? Who is winning? Who is doing it faster? What do you mean? Is this a real question? Ah, you mean who is doing it faster? Well, what is the real question, guys? No, it has nothing to do with experience. I mean, depends how you consider what you consider experience. Well, the real question is what, guys? How am I doing it so fast? That should be the real question. Well, that depends what you mean by experience, guys. Guess how am I doing it so fast? It's because I'm not doing it like you are doing it at all, right? I'm not going through the process that you're going through. I'm going from an entirely different and that's my point. Is if you mean experience, here's my experience. My experience is I know where I want to get. You see, and if I know where I want to get, I can take a very different route. So you take this route, a very long-winded route, and I'm just going there, right? So you're driving in a taxi in circles, so to speak, whereas I can get there much more directly. You understand? So the experience part is, I suppose, I probably can do it faster than you maybe if I do it your way, but it would not be that fast. I would not be able to do it so fast in 2 seconds if I were doing what you are doing. Ah, you say you want to know my secret now? Yes, I can, guys. But what I do is I know Calc 3. So I I use Calculus 3 to crush those questions. You see, so that's experience, yes, but not algebra. You see, not the algebra part. I will show you my way if you want to see it, but you will not be able to understand why it works without knowledge of partial derivatives. You see, I can come up with such a thing because I know what partial derivatives are. I can utilize those, you see. And and if you do it, that's my point in showing you how fast I can do it is if you do it consciously, thinking about it, you understand the subject and you can do everything very fast and nothing surprises you, nothing phases you. But if not, then the subject is every single minutia is a new problem. Good. So yes, you want to see what's the formula? You can write the formula, but make sure that not to be confused with what you understand. Do you want to see what I do? All right. So this is the situation, guys. Let me 1 second. So look at this expression, for instance. Suppose, let's say you have x squared plus xy, right? Maybe plus sine y is equal to 10. I don't know. Yes? This, and I have to find y prime. This is what I observe. I look at this full expression and I consider this as a function of two variables. This is f of x, y. In fact, I can always make it equal to 0. If I want to, I can always move it. Before I do that, I can always, if I want to, write it as x squared plus xy plus sine y minus 10 equal to 0. And then I look at this expression, and this expression is a function of two variables, x and y, equals 0. In other words, it uses two formulas, okay? So then there is the partial derivative. You can say the partial derivative of this function with respect to x is where I pretend that y is constant. Y is constant. You understand, guys? I'm worried about telling you that because I'm not sure. You have to understand the method that I explained, because that method is intelligible using calculate-1 techniques. Yes? But the procedure that I'm showing you in calculations is going to give a much faster result. Well, when you do implicit differentiation, when you say derivative with respect to f sub x, it's called partial with respect to x. It's going to be the derivative where y is just like the number. Imagine y is the number 5. So what you have is then 2x plus, what's the derivative of x times y, please? If I take the derivative only partial with respect to x. Don't be confused, guys. I hope it's not going to destroy your understanding of what I just explained. Y in this formula is a function of x, but in using my technique, I ignore that. I'm saying y is just like a constant. So what's the derivative of x times y? The derivative of that is going to be just y. Plus derivative here is 0, so that's it. It's just this is the derivative with respect to x. Now when I take the derivative partial with respect to y, now I pretend x is constant, because the derivative of x times y, if it's like 5 times y is now like 5 times x, the derivative is 5. Now the partial with respect to y. Again, guys, if you use this type of procedure when you cut corners, you use it at your peril. Make sure you understood what I explained. This I'm just showing you a procedure. So partial with respect to y, I pretend that x is a constant. So this is like 5 squared plus 5 times y. So what happens here is that they take the derivative here. That would be x. Derivative of sine of y would be then plus cosine y. Do you understand? So I first pretend that y is a number, then I pretend x is a number, and I have fx, fy. And then it happens always that the derivative y prime is negative of the fraction, the expression for x, divided by the expression for y. So so using Calc 3, you can have, or you can solve all those equations right away. It's always the derivative with respect to x, where I pretend I take the derivative with respect to x, divided by pretending that I take the derivative with respect to y. So the result will be what? The result will be 2, it's minus 2x plus y, divided by x plus cosine y. Yeah? You want to try another one like this? Yeah, of course I was cheating, exactly. I am no good dirty Russian, of course. The thing is, guys, I mean, you say it's cheating. Is it cheating? I mean, I understand why the formula works. You understand? I mean, you might be confused, like, well, what are you doing there? But I understand why. I don't remember the formula. I can derive it instantly. In just a few moments, I need to think about that. I think, oh, what was the formula? Ah, here it is. Right? The 10 doesn't matter. It's a constant. So here is another example. Okay, suppose we have x cosine y plus y sine x equal to xy. Okay. Remember that before you begin that, you want to make the expression equal to 0. So move everything to one side. So this would be x cosine y plus y sine x minus xy equal to 0. You understand? This is your function f, xy. Now you have to tell me what is f of x. All right, so the derivative with respect to x, yes, Francis, good. So that derivative with respect, the partial with respect to x is going to be cosine y plus y cosine x. Minus y, the partial with respect to y now. You have to be careful. You will forget the formula, you will misuse it. It always works, but if you don't understand it, you might misuse it. Okay, so, and besides the other thing, when you do the grunt work, it trains you with basic algebra, which is bothering you with other things. You understand? So you should be proficient enough to be able to do it with basic algebra. But if you're running out of time and you have this formula handy, I personally forget the formula all the time. I just always establish it. I can do that in my head. You see, I can understand why it's true. So if you take Calc 3 and understand why it's true, you would not have problems. What is Fy, please? Tell me quickly what is Fy. Okay, let's see. Yes. Are you ready, guys, with Fy? It's just you pretend that x is constant, so that would be minus x sine y plus sine x minus x. You agree? In other words, when I say f sub x, I'm saying x is the variable, y is constant. When I say f sub y, I say y is the variable, x is constant. So you can think of x equal 5 or whatever you like imagining. So then the derivative y prime is going to be minus the ratio of the x over the y, which is minus cosine y plus y cosine x minus y divided by minus x sine y plus sine x minus x. You can multiply the minus to the bottom or to the top. It's up to you what you do with it. Good. So that's the shortcut that I use. Now, you can check that those formulas are here. I obtained them using algebra. Do you see that? I actually carry the algebra. So when you look into my notes, guys, and I really advise you to still do it using the Calc 1 way, because it teaches you algebra, it teaches you factoring, it reminds you, it brushes your skills, it's very boring and annoying, but it makes you more efficient with the algebra. And you might be caught either for the final or for something else where this formula you will not remember correctly since you don't understand it. My way is easier, of course. Of course it's easier, it's faster, but I understand it. That's the advantage. I cannot go wrong using it, but you can go in so many ways wrong. Good. So here I show the Calc 1 technique, because the Calc 1 technique you understand. The Calc 3 technique, you do not understand why that works. So I would advise you to, at least for now, to use the old way of solving the question slowly, and then checking your work with the new way, with the formula. Use it to check your work that you did it correctly. Clear? You can try remembering, it's up to you, but it's not, you know. You see? Do you want me to go through any one of the questions, to do it slowly before I move on? Guys, this is a very difficult and important topic. So make sure that you are able to carry implicit differentiation the way it's taught in Calc 1. You understand? Up to you. I can solve one of those questions slowly if you like, or I mean, you understand the idea. Solving it slowly is just using boring algebra, right? You just move things around, divide, you know, right? Which you should be very comfortable with, but you are not. Right? You should, when you do that, when you expand parentheses, when you multiply, when you move things around, you should be able to do that fast. Do you want then last round? Anybody wants any one of those questions to be solved slowly? E. Okay, let's do E. I'll do it slowly. So let's see. So it's tangent x minus y, y over. Okay. I copied it correctly. I hope so. Let's see. Yeah, doesn't matter really, but okay. Let's go. So we take the derivative of that, guys. We do it together. But again, guys, I mean, I can do it. You have to practice, right? What does it matter that I do it? The derivative of this part is secant squared x minus y. We will do it both quick way and slow way, okay? So, this, and then the derivative of the inside is 1 minus y prime using the slow way. Now, on the other side, I can use quotient law. So it's 1 minus x squared, 1 minus x squared, the derivative of y, which is y prime, minus the derivative of the bottom, which is of this, which is minus 2x times y. Good? So what can I do next? I mean, I might as well multiply the 1 minus x squared across. So I write 1 minus x squared secant x minus y, 1 minus y prime, equal to 1 minus x squared y prime minus 2xy. You see, my goal is to have all the y primes on the left, all the non-y primes on the right. So what do? I multiply this full expression. You see, guys, so keep it intact. Don't labor too hard. This thing I will multiply in here and in here. So what do I get? I get that 1 minus x squared secant x minus y minus 1 minus x squared secant x minus y prime is equal to this. So then I move the things that don't have a y prime to one side and the things that do have a y prime to the other. And what do I get? I get, look at it, this has a y prime and this has a y prime. So I will get minus 1 minus x squared y prime minus 1 minus x squared secant x minus y prime is equal to minus 1 minus x squared secant x minus y minus 2xy. So there are lots of negatives there. So you see that, guys? With me? And then what? And then simply I can factor out the y primes and divide. So I have that y prime is equal to, let's see what's the numerator. The numerator here is 1 minus x squared squared secant x minus y. It's I multiply by -1 everything, so I can cancel it out. So it's really 1 minus x squared squared secant of x minus y plus 2xy. And on the bottom, I divide by, you see, I have 1 minus x squared plus 1 minus x squared squared secant x minus y. And this is my solution. Good? You all understand, guys, that it's just basically, it's just algebra and be careful. That's all it is. Yes, you can still do it fast. You agree? I mean, I talk over it and I wrote a bunch of lines which I would have not written for myself. Wouldn't 2xy be a plus? What did I write? 2xy is a plus. Am I okay? So let's see what we have here. So you see there is a minus and there is a minus here. I move the 1 minus x squared secant x minus 1. I move it across the equal sign, it becomes a minus. Yes, and here we have yeah. So so I can get rid of all the minuses there, I think. We can now verify using the quick method. We can verify whether my formula is right using the quick method. Remember that I had tangent x minus y. So I had tangent of x minus y equal to y over 1 plus x squared, correct? 1 minus x squared, I'm sorry. You're saying that here there should be a plus, right? Minus 2xy, so there should be a plus. So there is a mistake that I did make. Yes, there is a mistake. Some careless thing that I did here. It should be a plus because, because the derivative here is minus the derivative of the bottom. It's minus 2xy, so that should be a plus. And there is a place where I need to change it to pluses. So I think it's going to be 1 minus is changed to a plus, something like this probably. I believe it's going to be now right. Okay, let's check. So this is my function, and what do you get? So your function is you just write tangent x minus y over 1 minus x squared. So equal to 0. So you take the derivative with respect to x first. So you have fx is secant squared x minus y minus, here I can use again 1 minus x squared then we have the derivative of y is I'll do it slower so you see it. The derivative of y is 0, so it's the 1 minus x squared times 0, but minus the derivative of this function times y, which is 2xy, right? That's what I should be getting for the partial derivative of x. Check that I'm right. I use quotient law, and I know that y derivative of y is 0 because I imagine it to be a constant number. Now, the derivative with respect to y of this expression it's minus secant squared x minus y minus 1 over 1 minus x squared. Now I treated y as my variable and x as constant. So that means that my derivative y prime is negative the expression with the x, and then divided by this. Now I can get rid of the minus here and write it and multiply by 1 minus x squared. So I have here 1 minus x squared secant squared x minus y minus 2xy divided by 1 minus x squared secant squared x minus y minus, well, plus, sorry, 1 minus x squared. So yes, it's similar. I made a mistake here. That should be a plus here. Good. So just be careful, guys. It's easy to make a mistake. Very easy. Okay, so when you solve it, you can try to, here I also give you the explanation for what I do in Calc 3. You can see if you can use that if you find it useful. Now, I would like to say that you should be very careful. Like, look at this, guys. Dy dx is x squared minus 2x. So I want you to find dy dx, given that x squared minus 2xy plus y squared is minus 10. What would you do? One last question, guys, and we are done for today. Okay, Francis. Well, guys, you're thinking very long. You can solve that y prime is equal to 1 by simplifying it, but you will be wrong. Because look at this expression. This expression is simply a perfect square equal to minus 10. X minus 1 squared equal to minus 10. No square in real numbers equals to minus 10. So this equation is meaningless. There is no solution to it. And therefore, the derivative that you find is not going to do anything. You follow? So there is, of course, always a problem of whether or not your effort is in vain. Maybe the equation does not have a solution. I will not, because it's Calc 1, bother you with that. You just, you see, whenever I ask, it will always have solution, but there is a theorem, a very powerful theorem that tells you that if you can find a pair of numbers that you can plug instead of x and y that solve this equation, then locally y can be defined as a function of x, or x can be defined as a function of y locally in some small region. Good. All right, guys, so I guess go rest, and I will talk more during on Tuesday, I presume, unless you have questions.